Hi everybody, in this video we're going to be looking at section 4.6 titled rank, the rank of a matrix, something we'll get to a little bit later, but for now we'll start out with a definition for what is the row space of a matrix. The row space is the set of linear combinations of the row vectors, so we're going to be thinking about these rows of a matrix as vectors in the same way that we have talked about the columns of a matrix by as vectors, and it's denoted the row of A, the row space of A. So in example 1 that we start with here, we are given a matrix A, and we're looking at the rows of that matrix as vectors, and we're writing them as horizontal vectors because that just kind of makes more sense to because they're coming from rows. So the set of linear combinations of the rows of A, or the row space of A, that is the span, because that's where we get our linear combinations from the span of a set, of the set R1, R2, R3, and R4. So the span of that set is the row space of the matrix A. Next, we get Theorem 13, so lots of theorems in this section, or in this chapter, lots of definitions, lots of theorems. So maybe make some flashcards, just throwing that out there as an option or an idea. So in Theorem 13, we have if two matrices are row equivalent, A and B, then their row spaces are the same. If B is an echelon form, its non-zero rows form a basis for the row space of A as well as that of B. Okay, so the idea behind this proof, I'm not going to write a formal proof of this. It is in the book. You can choose to read through it if you want to. It hopefully makes sense that if A and B are row equivalent, their row spaces would be the same, because the row space is just the set of linear combinations of the rows. And when we do row operations, those are just linear combinations of the rows. So reducing a matrix into echelon form doesn't change the row space, because I could always do row operations, linear combinations, to go back to the other matrix, the previous matrix. All right, now in example 2, we're going to find three things. We're going to find first a basis for the row space, and then a basis for the column space, and then a basis for the null space of this matrix A here. All right, and what we can start with, or what we need to do first, is reduce our matrix into echelon form, because if I want a basis, I need to know if there's any vectors to throw out for the column space, any columns to throw out for the column space, or any rows to throw out for the row space, like if I get a row of zeros or a column missing a pivot. Okay, so when I reduce this to echelon form, it is, let's see, what do I get here? Where am I? 1 0 0 0 and 3 1 0 0 and -5 -2 0 0 1 2 -4 0 and 5 -7 and 20 and 0. And so we can see now that we have a row of zeros, we have a couple of missing pivots, okay, and we're just going to call this echelon form, we're just going to label that as B. All right, excuse me. So what we can do now with that work, with it just in echelon form, we can say, all right, now I know that I have a basis for the row space of my matrix A. Okay, what is that equal to? Okay, we're talking row space, so we're going across, and I'm going to write these vectors horizontally. The first vector is row 1, 1, 3, -5, 1, and 5. 1, 3, -5, 1, 5. That is the first vector in the row space. The second vector is 0, 1, -2, 2, -7. And the third vector in the basis for the row space, 0, 0, 0, -4, and 20. That's a 0. That set, those three vectors, are a basis for the row space. I can do linear combinations and produce any row, linear combinations of those vectors, and produce any row in my original matrix A. Okay, and notice I used the echelon rows. Okay, now when I go and write down my basis for the column space, of A, all right, that also is going to be three vectors. And I don't know if I said this a minute ago, but those rows Whoops, I didn't mean to scribble that out. Those rows in the row space are coming from those 3 pivot positions, right? The non-zero rows, the rows with pivots. Okay. Similarly, in my basis for the column space, my non-zero, not my non-zero columns, but my pivot columns, there we go. This first pivot column defines the first vector in my column space, but I'm going to go back to the original matrix A. So the first column in my original matrix A, -2, 1, 3, 1, is the first vector in the column space. And then my next pivot is in column 2, but again, I go back to column 2 of matrix A, -5, 3, 11, 7. And then the third vector in the column space comes from the 4th column, and then I go back to my original matrix A and write down column 4, which is 0, 1, 7, 5. And those 3 vectors make up the column space of my matrix. The number of vectors in the basis for row of A and the number of vectors in the basis for the column space, because they're both defined by where the pivots are, those should always have the same number of vectors. Now, for the null space, for the null of A, we need reduced echelon form. Reduced echelon form for the null space of A. All right, so I'm going to give you that, right, because you could just type in your calculator. The original matrix A is row equivalent to B, which is row equivalent to C, which looks like this. 1 with 3 zeros, and then 0, 1, 0, 0, and then 1, -2, 0, 0, and then 0, 0, 1, 0, 1, 0, and then 1, 3, -5, 0, 1, 3, -5, 0, and this is a 1 there. There we go. Okay, so that is my echelon form, or my reduced echelon form, excuse me. And from that, we can write down the basis for our null space. And the process for doing that, I'm going to take this top row and write down an equation, x1 plus x3 plus x5 equals 0. x2, it'd be minus 2x3 plus 3x5 equals 0. And the last one is x4 minus, oops, actually, no, that's right, x4 minus 5, x5 equals 0. Then solving for each of those variables, and we can see because of the missing pivots that x4 is free and x5 is also a free variable. But we can solve for x1 in terms of the free variables. We can solve for x2 in terms of the free variables, minus 3x5, and x4 in terms of my free variable, 5x5. There we go. All right, and then keep these, and then the lots of steps here. Our basis, now we can finally write down our basis. Maybe you might need another step in between. Do I want to write that? Yeah, let's do that. Okay, so I can write my x solution, x1, x2, x3, x4, x5. I didn't make that bracket wide enough. That's okay. Let's see. So x1 is negative x3 minus x5. x2 is 2x3 minus 3x5. x3 is free, so it gets an x3. x4 is 5, x5. And x5 is free, so it also gets just an x5. And then we can break that up and factor out the scalars. So break that up into 2 vectors and factor out the scalars, and we can write down the basis for the null of A. The basis for the null space is minus 1, 2, 1, 0, 0. And close that bracket and a comma. And then the other vector, the x5 vector, minus 1, minus 3, 0, 5, 1. And there's the basis for the null space of A. So in terms of like remembering how to do all of that, right, there's procedurally, first we get it into echelon form. Let me get my highlighter here, or my pointer. First we get it into echelon form, right? And then I can write down the row space, which comes right from that echelon form. I can write down the column space, which comes from the pivot columns, but I need to go back to the original matrix A. All right, and then to get the null space, need reduced echelon form, and that comes from the non-pivot columns, solving in terms of those free variables as we did here. All right, and now we get to the main topic of the section after we get that preliminary work out of the way, and that is the rank theorem. First, we'll define what the rank of a matrix is, right? It's the dimension of the column space of A. Oh, that's all the rank is. The rank of a matrix is the dimension of the column space. All right, and then we get the rank theorem, okay? The dimension of the column space and the row space of a matrix, m by n, are equal to each other. I mentioned that previously, but now we get that within the rank theorem. And then this common dimension, the rank of A, is also equal to the number of pivot positions, and it satisfies this equation here. The rank of a matrix plus the dimension of the null space is equal to n. And then another way to think about this, and just kind of a way that makes sense, right, hopefully, the rank of the matrix, also known as the dimension of the column space, oops, I can't spell apparently, column space plus the dimension of the null space is equal to n. But the dimension of the column space is the number of pivots, right? The pivots are that give us the column space, which is defined to be the rank of a matrix, plus the number. Okay, so where does the null space come from? The number, well, I can really not spell today, plus the number of non-pivots, that's equal to the number of columns. And again, that's kind of what I meant, why this should kind of make sense. The number of columns being the n there. Try that again. There we go. The number of pivots plus the number of non-pivots is the number of columns within my matrix. Hopefully straightforward. And then using the rank theorem, we can address questions like this that talk about, just a matrix based on its size, not actually working with it, and answer questions like that. So in this one, we have a two-dimensional null space, we have a 7x9 matrix, and then want to know what is the rank of that matrix. All right, so for answering part A, the first thing to kind of make a note of is that if A is 7x9, A has 9 columns. Right, a 7x9 row by column, so A has 9 columns, which tells me that I can say, all right, in my rank theorem, the rank of A plus, well, we have a two-dimensional null space, 2, the dimension of the null space is 2, is equal to the number of columns. Oh, okay, so the rank of A is equal to 7. And then for part B says, could a 6x9 matrix have a two-dimensional null space? All right, so how am I going to answer part C? Well, first, it also has 9 columns, so has 9 columns again. Has 9 columns. There we go. And so the rank of A, right, just kind of treating it the same as the last example, plus it has a could it have a two-dimensional null space? 2 is equal to 9. Rank of A is equal to 7. Okay, so this looks like it's the exact same as the previous problem. The rank would be 7, but there's a but coming. There's a big but coming, but maybe you can see what it is. Pause the video if you want to think if you can see what the but is, what the issue is. It comes from, well, what is the rank? We've talked about it for a couple of slides now. The rank of the matrix is the dimension of the column space, also known as the number of pivots, right? The rank of A is the number of pivots. Okay, so why do I run into an issue? The columns of, is it B? The columns of my matrix are vectors in R6 because I was told that it was 6x9. If the columns of my matrix are vectors in R6, how many pivots are available? I'm pretty sure only 6. Only 6 available pivots. So the dimension the dimension of the column space, abbreviating a little bit there, the dimension of the column space cannot exceed 6. That's the issue. So the answer really is a resounding no. And now to close out the section, we get to be reintroduced to the invertible matrix theorem and add even more letters of the alphabet onto it. So we get M, we get N, O, P, Q, and R statements added on to the invertible matrix theorem, and we'll go through just a quick little quasi proof of how they all tie in. But take a look at them first. The columns of A form a basis of Rn. Column space of A is equal to Rn. The dimension of the column space is equal to n, the number of columns. The rank of A is equal to n, because that's the same as the column space. the null space of A is equal to just the 0 vector, so there's no free variables, which we should know. And then the dimension of the null space is equal to 0. Okay, so the way that we're going to tie these in, first, the M statement is already there. It's just a new definition. So M is equivalent to E and H, right? You put those two together. E, I believe, is the one about span. H is about linear independence. And so that M already ties in because it's just it's using two previous definitions. Then for the rest, we're going to follow this sequence. We're going to go G in the invertible matrix theorem gives us N. If G is true, then N is true, which implies O, which implies P, which implies R to Q, and then back to D, because remember, we have to close the loop. So starting with G, which says that AX equals B, has at least one solution for each B in Rn. That statement implies N, so statement N, because, so B/C for because, the column space of A is the exact same thing as the set of all B. The column space of A is the set of all B such that capital A, AX equals B is consistent. So they're basically saying that G just leads us directly into statement N. And then N to O to P, N, O, and P. Oops, I missed my arrow there. N to O to P, those all follow from the definition of dimension and rank, right? Because the column space, the dimension of the column space, the rank of it, those are all very tied together with just a couple of definitions. All right, and then P to R, let's see. If the rank of A, so if the rank of A is N, then the dimension of null A has to be 0, and that's from the rank theorem, by the rank theorem. And also, if the dimension of the null space is 0, then null A is equal to just the 0 vector. So that gives me P to R and then to Q. And then finally, I'll write finally. All right, how do we tie it back into what we already have from the invertible matrix theorem? The null space of A being just the 0 vector means, means that AX equals 0. That homogeneous system has only the trivial solution. has only the trivial solution, which ties us back into everything else in the theorem. Okay, so now we're running out of letters in the alphabet here, guys. We've got all of these statements, things that we have encountered throughout this course for the last however many weeks. I don't know what week we're in, but they all tie into just this one singular concept of whether or not a matrix is invertible. That's the end of this section. Thank you for listening.